Welcome everyone. We are here to look at the T-SQL apply operator with Itzik. He's a SQL Server MVP and T-SQL trainer. He's going to explain about how the apply operator works and how it differs from inner join and other operators. I will hand it over to Itzik to introduce himself first.
Thanks, UC. So essentially the session is about the table operator, just like joins are table operators, also cross-apply and outer apply are table operators. And for some strange reason, it seems that the operator is off the radar for many people. It was actually introduced in SQL Server 2005 already. And back then when it was introduced, it was over a decade ago,
yeah.
Right? So, when I teach about T-SQL, I usually do a quick show of hands. How many people know of the apply operator? How many people already use the apply operator? And I see a very small percentage. So you see 20% of people maybe already know and use it. So nowadays, I use it in so many of my solutions that it's still a puzzle to me. But anyway, we're trying to fix this with this session and show you how powerful this operator is. And you will see that once you get to know it, it's one of those things that you cannot stop, using them. So just a few words about myself, and then UC will introduce himself before we actually start with the technical part. So I'm mainly a T-SQL trainer for SolidQ these days. I teach two main kinds of courses. One is an advanced T-SQL class that runs for 5 days, and another is a 4-day fundamentals class. So I basically travel around the world doing these kinds of courses. My background is about 20 years of experience with databases, SQL Server mainly. This is my expertise. And in the last decade and a half, I would say, my focus has been mainly the language part. So T-SQL and anything that has to do with making the T-SQL code run fast. So optimization side of things, tuning, physical structures, how to write efficient code, that's pretty much me. So I've written quite a lot of books about T-SQL and just starting a new one with the improvements in 2012 and 2014 as well. And let me hand it to UC.
Hi, my name is Umachandar. I am a program manager in the SQL Server product group. I'm currently working on Windows Azure SQL database. I started working with SQL Server since '94 and other database products. I'm familiar with most of the operators and T-SQL functionality in SQL Server. So back to Itzik.
So by the way, I don't know if you noticed the accent, but both UC and I have the same mother tongue, which is T-SQL, right?
Yeah.
And I feel more comfortable with T-SQL than any other language. And UC is one of those people that I think know T-SQL best on this planet. So we feel very, very comfortable communicating.
Yeah.
All right, so the course is organized as two main parts. So we have the first part where we provide the foundations, explain what the apply operator is. And to do so, we'll start by just remembering those very familiar join operators, cross join, inner join, and then relate this to the apply operator and show what kinds of things the joins are not capable of doing and the apply actually allows you to do. So this will be the first part, and I'll show a fairly simple example just to demonstrate this. And with this, we will conclude the first part, just essentially laying the foundations. Then the second part will be the bulk of the course. In this part, we'll go through different features that we have available in SQL Server. Each of them was introduced in a different version of the product. So we thought it would be interesting to show how features that were introduced in 7.0, in 2000, in 2005, 2008, 2012, that people use quite often, how we can boost them, how we can improve them by combining them with this apply operator. Right? So this will be the second part that will take the majority of the course, basically. All right, so let's get started with the first part about the foundations, but just to give you a sense about expectations, background that you should have before you see this session. So the course is intended for people that do have some experience already. The assumption is that you are familiar with the classic, let's say, SQL constructs, mainly joins and the subqueries, including correlated subqueries, which you will see a very strong relationship to the apply operator. So I'm assuming that you're very comfortable with joins and the subqueries, especially the correlated ones. And let's say that you have around half a year of experience working with the T-SQL, including optimization aspects. So you're familiar with the looking at query execution plans. You're familiar with what an index scan is, what an index seek is, what the lookup is, and generally you are comfortable with analyzing query execution plans. In terms of prerequisites, for one, I have a book that covers T-SQL fundamentals. I'm assuming that you have kind of parallel knowledge that appears in this book that describes the different constructs. And also, to download the source code for this course, you have a link in the slide to a website called tsql.solidq.com. And within this website, there's a section called resources. And within it, there's a section called source code for recent conferences and sessions. And anyway, you have also the direct link on this slide, right? So in general, the way the course is organized, I believe more in demonstrating code and less in looking at slides. I think people relate to code better and learn better this way. So in many of the examples, I will develop the solutions from scratch, showing how the thought process, involved in those solutions, right? So that's in terms of expectations. And then generally with the Microsoft Virtual Academy community, this is a free online learning tailored for IT pros and developers. There are already more than 1 million subscribers, and now there's a new course that you can obtain from this media. So let's get started with the first part, providing the foundations for the apply operator. And by the way, a nice perspective that we have with UC being here is besides being a program manager directly involved in T-SQL development and so on, and giving us the Microsoft perspective, also UC is a member of the ANSI SQL committee. So it would be interesting in some cases to talk about a relationship of the constructs that we will discuss to standard SQL and looking what the standard has to offer in the different areas, right? So let's get started with understanding, first of all, how joins are designed, and because the apply operator in some sense is similar to joins, for one, because it's designed as a table operator, just like a join is an operator that appears within the from clause of a query, apply is also a table operator that appears in the from clause of a query. So let's first get to look at how joins are designed, and then we'll talk about what are the limitations of joins and how apply gets to solve those. So let's start with a simple cross join as an example. Then let's look at inner joins, and then we'll understand how apply relates to them. So if we look at the cross join as an example, a cross join essentially gives us the combinations of the rows from both sets. So we go and write a query, select some columns from some table. Let's say that we had a table called the T1, and we had these columns from this table, and we have another table called T2. So select from some table T2, and now I wanted to go and return all combinations from these two tables. I would go and write a select from a T1, and then a cross join with a select from some T2, and then go and collect elements from the different sides. So T1 column 1, T2 dot column 1, and then basically what we would get are all combinations of rows from the two sides. So if I have 5 rows in T1 and 10 rows in T2, we're going to get 50 rows basically in the result. So as a more concrete example for a cross join, let's say that we have a table holding information about customers. So I'll use a sample database called T-SQL 2012. And by the way, in the source code that you will download, you will see links to download specific source code to create different sample databases that are used within the demos, right? So just make sure that you install them before you run the example that I'm demonstrating. So T-SQL 2012 is a sample database that is based originally on the Northwind sample database. It's a database that Microsoft used for both Access historically and for some previous versions of SQL Server. And this sample database is built basically on top of the Northwind database. So we have a table holding information about customers. And then within this database, I also have a table function called getNums. getNums is a very handy auxiliary function that accepts as inputs some kind of a low value and some kind of a high value, and it simply generates a sequence of integers within this range. So for example, if I provided 1 as the low value and 10 as the high value, you see the result consisting of 10 numbers. Now, let's suppose that we need to generate a report that shows activity for customers in different years. And I first need to generate this kind of template for my report that has a row per customer and a column per year in the range 2012 to 2014. So from the function, I will go and collect the years 2012 through 2014. And now what I want to do is take all customers and all years within this range and then generate all possible combinations. And that's exactly where a cross join will help us. We'll go and say select from customers, and maybe let's call it C in short, and then do a cross join with our DBO getNums function, providing the years 2012 through 2014 as the inputs, and this will be Y for years. And then from the customer side, I'll collect maybe the customer ID and the company name. And then from the Y side, I'll collect the number representing, let's say, an order year. And now you will see how we get 273 rows, because it's 91 rows in the customers table and 3 rows in our years table. So to summarize, what a cross-join is, we use 2 predefined sets as our inputs. And then the cross-join simply gives us the combinations of these 2 sets. So 3 rows in one, 91 rows in the other, and then we have 273 rows basically in the combination. So the critical thing to remember about the join part before we relate it to the apply operator is the fact that the 2 sets are predefined. It's not that one set is evaluated first and the other set is evaluated second. It's not that one set is evaluated based on elements from the other set. Think about 2 sets or 2 relations that are predefined, and then we go and generate all combinations, right? So this is pretty much a cross join. Then let's talk about an inner join. An inner join also gives us 2 sets that are predefined, but then as if we generate all possible combinations, but then apply some kind of a predicate, some kind of a condition that gives us only matches that are based on this sort of condition. So, for example, if I take our customers table, and then I'll take the orders table. So remember, in the customers table, we have 91 customers. In the orders table, we have 830 orders, and you will notice that the orders were placed by some customer, of course. And now we want to go and connect customers and the related orders. For this, we have an inner join. So what we will do is we will say select from sales.customers. Let's call it C in short. Then do an inner join between sales customers and sales orders. And then we have a predicate, what we don't have in a cross join, that relates the orders to the respective customers. So c.custid equals o.custid. And in some literature, the way an inner join is described is actually as if we have first a cross join between the 2 relations, and then we apply a predicate that filters the rows from this Cartesian product that we have from the 2 sides. So now we can go and collect from the matches and information that we like the customer ID and the company name from the customer side, and then from the order side, let's collect the order ID, maybe the order date, and so on. So you will see that what we get in the result are only the matching combinations. So again, what's special about the inner join, for one, like the cross join, it is concerned with two predefined sets. So also here we have a predefined set of customers, a predefined set of orders, and then we have the extra that we don't have in a cross join, which is a predicate that filters only the interesting matches. All right? So in both a cross and an inner join, we can say that the two input components for the join are predefined sets. And now let's try and think about what the join cannot do. And for this, we will use the apply operator to solve our problem. So what the join cannot do is take one set that is predefined, but then have the other set be created separately for each row in the left set based on elements that we collect from the left set. So if this doesn't make much sense, let's look at an example. So for example, let's say that instead of matching all orders with the respective customers, what we want to do is for each customer, we want to return only a certain number of its most recent orders, right? And let's say that we have a query that for a given customer returns a certain number of most recent orders. So let's do it like this. We write a select top of some number. Let's take 3 as an example of information about the order. So order ID, order date, maybe the employee ID from orders where the customer ID is equal to some specific customer. So here you can see that I returned 3 orders for some customer, and now to make those the 3 most recent orders, the top operator will need an order specification. So we say order by order date descending, and then order ID descending. And as you can see, what we got now are the 3 most recent orders for customer 1. And now let's say that I want to encapsulate this logic within a table function. So I'll go ahead and create one. So just to make sure we don't have one already. And now let's go ahead and create a function called getTopOrders that accepts a customer ID as input, as well as a number of most recent orders that we want to return. And then the function returns a table. And what it has is just a return clause that returns the result of this query, only of course referring to the input parameters that we pass to the function. And just an important note before we talk about how we involve apply in this is that this particular example is not that critical to understand the apply operator. I'm just using it as a vehicle to demonstrate the idea. But just think about any kind of table expression or table function that its logic could be essentially anything. In this case, it happens to be return the n most recent orders for a given customer, but think about any table function that returns any kind of a result set. So now that our logic is encapsulated in a function, if I wanted to go ahead and return the 3 most recent orders for customer 1, I would say select from our function and then pass customer 1 as input and the number 3 as input, and then the result, as you can see, are the 3 most recent orders for the customer 1. Now imagine that, never mind how the logic was implemented within the function, I wanted to go ahead and return the 3 most recent orders for each of my customers. Now remember that both in a cross join and in an inner join, the sets have to be predefined. Here what I want to do is I want to go and query the customers table as my left set. Let's call it C in short. Now I cannot say cross join and then my function, because the inputs to the function are not static inputs. I actually need those inputs. Let's call it maybe O for order. So the inputs are supposed to be inputs that I'm collecting from the left row. So CCast ID as the customer ID, and the number 3 in this case would still be the constant number. Why can't this work? Because this element I need to collect from the left row, and the left row therefore has to be evaluated before I'm activating the right side. So in a sense, what I'm looking for is something similar to a cross join, but such an activity that will evaluate the left set first, and then for each of its rows, will go and apply the right table function. So in a sense, it's like performing a cross join per row from the left side separately, but first look at the left row, evaluate it first, collect some element from it, and then activate the right side, right? So if you try to do a cross join here, let's go and actually try to see that it doesn't work. So let's return cast ID, company name from the left side, and then from the right side, let's return the order ID, the order date, and maybe the employee ID. And now let's make an attempt to run this query. And notice we get an error saying multi-part identifier CCAST ID could not be bound. The meaning of the error is that we're trying to refer to something that as if doesn't yet exist. Because remember, in the cross join, both sets have to be predefined. And it's not like we can rely on a component or an element from the left side when we are evaluating the right side. So in essence, we need something very similar to a cross join, but one that does the left side evaluation first, and then the right side is activated kind of per row from the left side, right? And that's exactly where cross-apply solves our problem. That's exactly what cross-apply does. So now we go evaluate customers first, as if we look at each row in the customer side separately, and then collect an element from the row, pass it here, and we can think of this element much like a correlation. Take the customer ID from the customer row, then evaluate the right side. For that row, generate the result, and then look at another row. Now, in reality, it's not like it has to happen like this, that we look at the left rows one at a time. In reality, or I should say more conceptually, actually, the evaluation does happen in this sort of all-at-once manner. So try to visualize all customer rows in this all-at-once manner, and that this right side gets applied to each of those as if at the same point in time. Of course, for many people, it's easier to think in terms of a cursor, as if we went with a cursor against the individual rows within the customers table, collected the customer ID, activated the function, generated the result, and moved on to the next customer, right? So when we go ahead and run this, then you can see how for customer 72, we got the 3 most recent orders. For customer 58, we got the 3 most recent orders. And then the part that is similar to a join is that we can return information from both sides. We can return elements from the left row, the customer row, and we can return elements from the right side, and that's the order itself, right? So that's in essence what the cross-apply is. So what we looked at is the most basic form of a cross-apply. We go and look at the rows from the left side and apply the right table expression, or in this case, table function, against the different rows in the left side. So this is the so-called cross-apply operator. Now we have a couple of other versions of the apply operator. One thing that the cross-apply does not return is, imagine that we have some rows in the customers table that simply don't have any related rows in the order side. In that case, the left row is actually discarded. So in this sense, it's actually similar to an inner join. If we have a customer that doesn't have any matching orders, an inner join does return such a customer. In a similar manner, in a cross-apply, if the customer gets 0 rows back from the function, then the left row, the customer row, is not returned either. By the way, the cross-apply operator is an operator that is specific to T-SQL, but I was wondering, Yussi, if there's anything in the standard that is similar to the apply operator.
Yeah, the standard actually has a different operator by name lateral. It's the same thing as apply. When we designed the feature at the time, some of the versions of the standard were still in draft. So we went and basically picked a name for it.
You would write it in a similar manner? So
yeah, so if we were to write it in ANSI standard, essentially this will just say lateral instead of...
So something like this, cross-join lateral?
Yes. So basically it's considered like a table operator, and that's how it would kind of look. We still have an opportunity at some point to probably introduce the standard specific syntax.
Right. So in other words, if anyone is migrating a system from another platform, more likely they will have lateral and they will need to convert it to this cross-apply, basically.
Yeah. Today, I think only Postgres probably implements it. DB2 doesn't. I mean, nobody has this. So, yeah.
All right. Cool. So now let's look at the second version of the apply operator. So remember, cross-apply, if we have a left row that doesn't have any rows coming back from the right side, then the left row is not returned either. So much like there are different versions of joins, we have a cross join, we have an inner join that returns only matches, and then we have an outer join that preserves rows from what we marked as the preserved side. If we said left outer join, we mark the left side as preserved. In a similar manner, we have an outer version of apply that simply says do not discard left rows if they get 0 matches from the right side. So let's say the cross-apply operator that we used returned 263 rows. We have a couple of customers that don't have any related orders. So now let's go and change it to outer apply. And now we should find a few extra rows. So you see now the number of rows returned is actually not 263, it's 265. So we have there a couple of extra customers. We can scroll down and look for them here. So you can see, for example, customer 22 has no related orders, and this time we did preserve it, unlike with the inner apply. So you see, it's a bit interesting why you decided to call the cross-apply operator cross-apply, not inner apply, if actually cross-apply behaves, it seems more like an inner join, that if there are no matches, it doesn't return the row.
I don't know. There is no real reason other than probably some of the implementation.
So
how we parse the syntax and so on.
But in a sense, it does seem like cross-apply does something similar to a cross-join, but per row.
Yeah, I mean, right? And the other reason is if you look at the syntax, just like cross-join, the predicate is not specified immediately after the join operator, right? Whereas an inner join and on clause is kind of mandatory. And here, by referencing the left side input, you have an implicit join.
Right.
I mean, you could still apply a further predicates by putting a where clause.
Right.
In that sense, it's more closer to a cross join. Because the typical case would be just you pass, like here in this example, like a customer ID, right? The column as reference.
Yeah, so maybe an easy way to try and visualize this is if I look at the customers table, to try and relate it to a cross join, I'll pick one customer, then I'll go invoke the function.
For that
I'll get,
customer,
let's say, 3 rows, and then it's as if I'm doing a cross join between this one row from customers
and then all the 3. Yeah.
So in this perspective, it's actually more similar to a cross join. So I guess we could essentially do a cross join indirectly by doing a cross apply just without any predicate.
Yeah,
so something like
sure.
So this effectively should give me exactly the same thing as a cross join, right?
Yes.
Yeah?
Yep.
So we have 75,530 rows because we're multiplying 91 rows in customers and 800
There is no
rows.
implicit reference. It's like basically everything from left side.
So in the standard, therefore, I imagine, or those platforms who did implement the lateral operator, I would imagine this should look something like a outer join.
So you just say...
So
that one would be outer join.
Outer join.
Lateral.
And then lateral.
Yeah.
And then actually you still would need the predicate, right? So some dummy predicate like...
Which is like 1 equal to 1.
1 equals 1.
Yeah.
So this is how those platforms that implemented an explicit lateral, that's how it would look like.
They're basically in the standard, it's defined as a table reference.
Right.
Whereas we implemented it as an operator. So, I mean, I guess that's probably where the difference comes from.
All right, so it's still quite easy to migrate.
Yeah, sure.
So it's pretty straightforward.
Easily transform the syntax, yes.
All right, so this would be the outer apply operator that basically adds a logical phase to the cross apply operator where we preserve the left rows even if we didn't get any matches back from the right side. And then there's a third version of the apply operator, but one that doesn't explicitly use the apply operator anyway or anywhere, but still the logic and the concept is very, very similar to apply. And in fact, before the apply operator was added to the engine, actually this activity didn't work. So let's see what is this sort of implied apply or implicit apply. So let's say that we wanted to go ahead and query our customers table and return the customer ID and maybe the company name. And now, in addition, I want to return for each of my customers also how many distinct employees handled the customer's last X orders. Let's say last 10 orders or last 3 orders, yeah? So how many employees? Now, I know that if I used an explicit apply, I could obtain each customer's last 10 orders by going and doing an apply to my function, right? So I could go ahead and say select, let's take employee ID from sales get top orders. And then remember, we pass some kind of a customer ID, we pass how many orders we want, and then what we get back are those orders. So here you can see the different employee IDs that appear in the customer's last 10 orders, if there were 10 orders. Of course, in this case, you see there were fewer orders. And now I could obviously go and say count distinct employee ID in those orders. So what I want to do is I want to take this logic, and instead of applying it to the constant one, I want to apply it to the customer ID that I'm collecting from the customer's table. So basically placing it right over here in this sort of, in a sense, correlated table subquery, right? So what I'm doing here is, here I'm passing CCAS ID from the customer's table. Even though I'm not doing this using an explicit apply, it's the exact same concept like apply, because essentially I'm applying the table function to each row from the underlying table in the query. And as you can see, it simply works. So customer 72 had 7 distinct employees handling its last 10 orders. Customer 58 had 5 distinct employees handling its last 5 orders, and so on. So this is what I will refer to later in the course as this sort of implicit apply, where in a sentence what we are doing is we are referring to a table function within a subquery, and we are passing a column from the underlying table as its input. Same idea, same technology that is used to process apply is used also to process this kind of activity. All right? So that's in essence implicit apply, and this pretty much concludes the first part that provides the fundamentals for the apply operator. So quite a strong operator, I would say.
Yep.
You know, so
very interesting and quite powerful too.
Right, and I believe you added it to the product in conjunction with the addition of all those dynamic management views, functions, and so on, where it can be very handy, right?
Yeah, especially where you want to correlate, like from tables to columns, or various DMVs which collect or which require certain input from outside, right?
Right.
So you could filter those and then.
Right. Yeah. Maybe one example that pops to mind is there's a dynamic management function that returns attributes of a query plan.
Mm-hmm.
It's called sys.dm exec plan attributes.
Yeah,
and then you have a DMV called sys.dm exec query stats that gives you the different performance statistics for queries, and there is a plan handle
and
that
then
you can
to pass that,
go ahead and pass it to the DM plan attributes, right?
Yep.
Yeah.
So it's quite useful. Yeah.
All right. So with this, we conclude the first part about the apply operator and its fundamentals. So to recap, we had the cross apply that returns the result rows from a function that we apply to each row from some left table, but does not return the left row if the right side returns an empty set. And then we have outer apply that, in addition to what cross apply does, preserves the left rows, even if they got 0 rows back from the right side. And then we have implicit apply, where we refer to a table function within a subquery, and we pass a column from the underlying table as input. So even though we're not saying apply anywhere, we're using essentially the same technology.
Thanks, Itzik, for a great overview of the apply operator. In the second session, we'll go and look at specific examples of how apply operator works with various new features added in SQL Server over different versions. Welcome everyone. We are now going to look at the apply operator and how it works with various features that were added in SQL Server. And if you haven't checked out the module 1, please do so for the apply operator fundamentals. Now I'll hand it over to Itzik to go and do a drill down on each of those features.
All right, thanks, UC. So essentially in this part is where we have the sort of meat of the course. The section covers uses of the apply operator to improve and enhance existing T-SQL features, each of which was added in a different version of the product. So I thought it would be nice to see all kinds of features, some of them that you use very likely quite often for many years, and how we can take apply and make them even better, right? So we'll actually start with SQL Server 7.0, or a feature that was introduced, I should say, in SQL Server 7.0. There's a top operator that is used quite commonly in queries to filter data. And we'll first look at the limitations the top has, but also we'll have a look at a certain common need that is very much related to top kind of filtering, and then look at the kind of optimization that we want our solution to get, and then in the different circumstances, what kind of solutions to use, and what are those circumstances where the solution that uses apply tends to excel. So this will be improving a 7.0 introduced feature. Then SQL Server 2000 introduced user-defined functions, and within those we have scalar user-defined functions. So a particular class of those scalar functions where we have a single expression involved, of course, is a very useful tool to have in the language, but then again you will see that we have quite a significant performance problem with those functions, and then how we can use apply to improve the performance. Then SQL Server 2005 introduces partitioning for tables and indexes, and we will look at the class of queries that don't get very good optimization, and again how to use apply to kind of get a workaround for those optimization issues. Then SQL Server 2008, there we will have a look at a very elegant construct called table value constructor that is a standard feature that SQL Server 2008 introduced, and then we will look at how to use apply to overcome two main things. One is a very, very fundamental limitation in SQL, not just T-SQL, but rather standard SQL in general. And then we'll also look at all kinds of unpivoting tasks where we need to unpivot data from a state of columns to a state of rows, but then see how the built-in unpivoting functionality that we have in SQL Server is limited, and how apply helps us solve those problems. And finally, SQL Server 2012 introduced the offset fetch feature. So a standard feature that is similar to the top operator, but then has some more functionality for paging purposes. And then we will have a look at how to use this offset fetch feature combined with apply to solve very classic statistical related calculation, median, in a more efficient manner than any other solution that I know of today. All right, so let's get started with the first part, looking at the top operator and then seeing how to use apply combined with top to solve a certain type of problem in certain circumstances very efficiently. All right, so let's take a look at a very kind of classic need that we have, known by many people in the SQL community as the top n per group kind of task. So imagine that we needed to go and query data. We have a table called orders in our sample data in a database called the T-SQL 2012. And by the way, the source code for this course, as I mentioned in the first module, is available for download. So you will be able to run the script that creates the sample database and use the same code samples yourself. So we have a table called orders, and we're about to collect some information from this table. Now imagine that I wanted to go ahead and return the 3 most recent orders. I could just add the simple top filter, and say, give me the top 3 orders, order by, order date descending, and in case we have ties in the date, let's say we want to break those based on the primary key value, the order ID. So I have a simple way to filter the 3 most recent orders in general, but I don't have a way to say I actually want to filter the 3 most recent orders for each of my customers. So what we are missing in the top operator is some sort of a partitioning element or a group element. So imagine if we could say a top 3 and then with some extra element within that filter being able to say partition by, let's say, the customer ID. So that's the kind of piece that we're missing. I want the 3 most recent orders for each customer, right? So not having this feature, we need to think about workarounds. Now, there's one very typical workaround that people use based on a row number function that numbers the rows within each customer group based on date and order ID descending, and then go ahead and filter only the rows where the row number is less than or equal to, let's say, 3 in this case. But let's think of the circumstances where the solution tends to perform well. So if the first module in this course focused more on the foundations of apply, now we're getting talk a lot about optimization aspects as well. So let's try and first look at the optimization for solutions for this task, and then think about in which circumstances each solution will tend to excel. So first, in terms of indexing, the kind of index that will be optimal for any kind of solution that you will use for this kind of top n per group task is what I like to think of as a POC index. And in POC, what I'm referring to is P stands for partitioning, O will stand for ordering, and C will stand for coverage. All right, so in a top n per group task, the per group or the group element is our partitioning element. So if we are after the 3 most recent orders per customer, our partitioning element in this case will be the customer ID. So that's our P part. Then the second part, ordering, is the ordering element within the task. And in our case, the ordering element is clearly order date descending followed by order ID descending. So we can go ahead and mark this element as the ordering element. And in this case, it happens to be a composite element. And then coverage essentially refers to all remaining elements in the query. So if I need to return in my select list also the employee ID besides the customer, order date, and order ID, employee ID becomes my covered element. And if I want to create an index that covers the query, that prevents the need to go outside of the index and perform expensive lookups and so on, we will ensure that this element is part of our index, and we could place it in the include clause because it doesn't play any role that cares about order, just coverage. So in our case, the C part is employee ID. So the POC index would have the P and O components in the key list and the C component, the covered element, in the include clause. By the way, a good friend of mine, Adam Mechanic, once tried to talk about this POC index in front of some audience, and he said that the POC acronym didn't catch very well. It wasn't that easy for people to remember, so he tried to use the term POCO for partitioning, ordering, and coverage, the CO part, and it seemed to catch better. So if it makes it easier for you to remember, you could use POCO. So thanks, Adam, for this finding. So anyway, let's go ahead and create this POC index. So create index. Let's call it IDX POC on our orders table. And then remember, customer ID, that's the P part, comes first. Then the ordering element comes second. And then we'll have an include clause, employee ID. All right, so now that we have our POC index, let's talk about 2 main data scenarios in terms of the sort of density of the partitioning element, customer ID in this case, yeah? So we'll discuss both low density case and high density case and think about what kind of plan we are hoping to get, and then what kind of plan we get in practice and how we achieve the kind of plan we're hoping for. So as an example for low density, we have lots of distinct customer IDs, each appearing a fairly small number of times. So just for the sake of the example, let's say that we have 10 million orders in total. And those 10 million orders are made of 1 million customers that each in average place, let's say, 10 orders. So in total, we have 10 million orders. An example for high density, and on purpose, I'll use a very extreme example, so it would be easy to see which solution works better in each case. So let's say that we have only 10 partitions, like 10 customers, and then each over the years placed 1 million orders. So again, we have 10 million orders, just the distribution here, the density is different. Now, in more realistic terms, it's very likely that you would find in many businesses a lot of customers each over the years placing a fairly small number of orders, even though, of course, the numbers will vary depending on the type of business. And cases of very high density, more likely you will find, for example, when we're talking about a similar task, but instead of customer orders, shipper orders. So think about most organizations having a very small number of shippers that they work with, but each over the years handles a very large number of orders. So, I mean, you could replace the partitioning element in your case with whatever is relevant to you, of course. I will use the customer order scenario, but you could think in other terms, obviously. So if we take a look visually at how the index is organized, our index will look like this. The row size, I would say, is about, we have 4 columns. There's an integer, date time, integer, and employee ID is integer. We're looking at roughly, I would say, 30 bytes per row. So we can fit somewhere around 300 or so rows per page. And this means that we are looking at roughly 30,000 pages in the leaf level of our index B tree. So let's go ahead and write it down, that we have about 30,000 pages, right? So within those pages, when we have very low density, then we're looking at lots and lots of very kind of short segments within the leaf, right? Each such range represents a different customer, right? So this would be customer 1, then this would be customer 2, and so on. So let's say customer 1 has 10 rows, customer 2, 10 rows, customer 3, 10 rows roughly, right? And then in the case of very high density, you would have a very small number of such sections, but each will have 1 million rows, right? So you would have 10 such ranges, and each with about 1 million rows. So now let's think about low and high densities and what kind of plan we are hoping to achieve. So in the low density case, certainly we do not want to see a plan that will perform a seek within the index per customer. Why? Because having 1 million customers, this would mean that you would get something like 1 million seeks. And let's say we have 3 levels within the tree. 1 million seeks would mean about 3 million random reads, right? So think about in the low density case, using a strategy that does seeks, or let's call it a seek per customer, you would be looking at roughly 3 million random reads. Now let's talk about a different possible strategy. A strategy that instead of doing a seek per customer, will go ahead and do just one ordered scan of the index and filter the interesting rows as we scan the index. So we know that we have about 30,000 pages within the index, and therefore a strategy that uses a scan in this case should give us, well, 30,000 sequential reads, right? So here there's no question about the fact that this is the kind of plan that we are aiming at, right? How do we achieve such a plan? Well, for this we use the strategy with the row number function. So what you would do is you would go ahead and add to your query, let's get rid of the top in this case, you would go ahead, return the customer ID along with the rest of the interesting information, then add the row number computation, over, and then partition by the customer ID, and then order by, we have our ordering elements, order date descending, followed by order ID descending. Let's call it row num. And now have a look at the kind of query plan that this query will give us. So we have the show actual execution plan turned on, and notice we get exactly the kind of plan that we were aiming at. Namely, we have an ordered scan of the POC index. You can see here that the ordered property of the scan is true. So we're scanning the leaf level of the index from head to tail. And then the segment and sequence project operators compute the row number function. The segment operator is responsible for the partitioning element of the row number function. So it just flags the next operator where a new partition starts. And then the sequence project operator simply increments the value as long as they're not the first row in the partition, and assigns a 1 if it is the first row. So you see that there's very little work involved in the computation of the row number when the data is already sorted by the partitioning and ordering elements. So most of the cost, as you can see, is here in the scanning of the data. That's about the 30,000 reads we're discussing. And now one extra element is to add a filter. So we will go ahead and define a table expression based on this query. And then in the outer part, we will return the interesting information from our table expression, and then simply add a filter that says where the row number is less than or equal to 3. And here's how we got the kind of plan that we were aiming at. You will see just one addition to the plan, and that's the extra filter that keeps only the rows where the row number is less than or equal to 3. So this is the desired strategy when we have low density. But now think about a case where we have very high density, like 10 customers, each with 1 million orders. The row number function gets optimized always in the same manner. It's not like, depending on the density of the data, the optimizer would go ahead and choose a different strategy. You would always get the full scan, and if the index already sorts the data in the right manner, at least there won't be any sort operator involved, but it will always be a full scan. But now, clearly, a far more efficient strategy when we have only 10 partitions would be one that does a seek per partition. So now we do want to see this kind of plan that does a seek per customer, and if it happens only 10 times, plus doing a scan of the first 3 rows containing the 3 most recent orders, we will get the whole work done with something like 10 seeks, and this means about 30 reads or so. So now, comparing these two strategies with a high density case with the seek per customer, you would be looking at not 3 million reads like before, but rather only 30 reads. But with the scan strategy, you would still be looking at 30,000 reads. So it's interesting to see here that it's not like one solution always works best, but it works best in certain circumstances. And here, clearly, we do not want to stick with the same solution, because otherwise we would still pay the 30,000 reads. We'd rather pay only 30 reads. So how do we achieve this? Well, we know how to achieve this for a single customer. We can write a simple top query, right? So we will say select top 3 and then the interesting elements. So order ID, order date, emp ID from sales.orders. And then where the customer ID is equal to a particular one, and then order by the ordering element, so order date descending, and then order ID descending. So you will see in the query plan that we're getting exactly the kind of plan that we are aiming at. Namely, you see a seek that goes to the beginning of customer 1 section in the index, and then a range scan proceeds 3 rows and then stops there. Why does it stop? Because it's the top operator that keeps requesting those rows, and it keeps requesting rows only 3 times. So after 3 rows, the scan doesn't continue essentially. So if we have 3 levels in the tree, we're looking at 3 reads. Now the question is, how do we apply this logic per customer? And as you could guess, you use the apply operator. So any kind of rhetorical question that I'm going to ask next, the answer is going to be the apply operator, essentially. So let's go ahead and use apply. Now, if you watch the first module that described the fundamentals of the apply operator, I actually showed how to encapsulate this query in a table function that accepts the customer ID and the number of rows to filter as inputs, and then we used a cross-apply operator to apply it. But you know, the applied component doesn't have to be a function. It can be any type of table expression, any type of table reference, including sort of a correlated derived table. So you would say select from customers, then you would do a cross-apply. Now have something that looks like a derived table, but the main thing that will be different here from a normal derived table, which is exactly the advantage that we have in the apply operator, is that we are not limited here to a predefined static relation. Rather, the right side can be sort of correlated to elements from the left side, right? So remember, it's as if we're looking at the left row first, collecting elements from it and using them to construct this table expression. So instead of using the constant customer 1, we will give a name to the inner table, O, then have the O cast ID being equal to, now the correlation, C cast ID, right? And then basically this table expression that we named A gets applied to each row from the customer's table. So we will be getting the 3 most recent orders for each customer, and with the query plan that does a seek per customer. So from the C side, we will return cast ID, perhaps the company name. And then from the A side, it's quite all right to return everything because we listed those elements explicitly here. And now let's go ahead and run it. And you see we get the same result, obviously. But then look at the query execution plan. Now this is the plan that we are essentially aiming at. You can see how the small customers table is scanned. And remember, in our theoretical example, we have only 10 customers. So this scan would involve just something like 1 or 2 page reads. And then the loop will run 10 times. And in each round, it will go and perform a seek to the beginning of the current customer section in the index, and then scan 3 rows, and we are done. So this will be the example that will give us 30 random reads, right? So here's an example of how to use the apply operator. Remember, in the top n per group problem, when the density of the partitioning element is very high, and we have a POC index that we prepared to support the solution, right? So you see, I'm kind of curious. Don't you think this is something that could be theoretically possible for the optimizer to detect itself, kind of looking at the data, seeing if it's dense or non-dense, and use it?
Sure, yeah, we could. But if you look at your query, like,
right?
I mean, one of the things we will do is like parameterize, right? Like you have a row number filter.
Right.
So, I mean, you specify a const value 3 there, but the typical case is to parameterize that query and say, okay, the row number can be anything, right? 3
right.
to 10 or whatever, right? And so the optimizer looks at, okay, can I satisfy all possible inputs
right.
by default? So, I mean, we could look at some hints or something, or even look at specific, sniff specific parameter values and then...
Right, so I mean, obviously, if you parameterize it, then we go to kind of typical parameter sniffing issues.
Yeah.
But, I mean, essentially, if you looked at a particular case, you could theoretically analyze the density and choose the right plan.
Sure.
But what I guess could be a bit difficult here is the fact that the plan that uses the apply needs this sort of driver table, right? Like the customer's table. Mm-hmm. And here, if you wrote it, never mind with the row number function or that doesn't involve the customer's table, you would still somehow need to figure out how to do sort of zigzagging between the levels.
Correct, yeah.
So there's some complexities here for sure.
Yeah. I mean, so
and also I imagine that the more logic you add to the optimizer, the more
I mean, you don't want to add like very specific logic for specific scenarios.
Yeah.
Kind of get like more 80% case rather than the 20% case.
And here it's quite straightforward for us to
I have to
go ahead
rewrite
and get
specific
this plan.
queries. So that's really
All right. All right, cool. So this pretty much concludes the first part about how to improve the top operator that was introduced in SQL Server 7.0 using the apply operator for very dense partitions in a top n per group task. All right, so we are moving on to the second segment that covers how to use the apply operator to improve a feature that was introduced back in SQL Server 2000 and also very, very widely used, and that's user-defined functions. And here we will talk about a specific case for user-defined functions, ones that are scalar and that are based on a single expression, right? So here's the story. Let's suppose that we want to write some kind of a query that involves computation, and there could be cases where we want to somehow encapsulate the computation in the function to hide the complexity and so on. So for the sake of this example, I'll use another sample database called performance. And by the way, also the source code that you will download for this course has a link to a script that creates the performance sample database. So if you want to run those examples in your environment, make sure that you download and run this code. So within the performance database, I have a table called orders, and this table has 1 million rows. So it's not a very big table, but kind of big enough to discuss performance aspects. So let's say that I have a simple query that I wanted to run. I want to go ahead and say, give me only those orders where the order date happens to fall on the last day of a year, right? So if, for example, the order date is February 12th of, let's say, the year 2007. So we want to return the order only if it's the end of 2007. And in this particular case, it's not. But if the order was placed on 31st of December 2007, we do want to see it, right? So first of all, let's look at one way to go and compute the last day of the year for a given input date. So let's say that we had some kind of an input date. And in this case, let's say that the data type of the input value is a datetime data type, which is the case for our order date column. And for now, let's just assign it with now, right? And now I want to go ahead and see what's the respective end of year for this input value, right? So one way to compute the end of year for a given date is the following. Imagine that we had this sort of timeline. And on this timeline, each mark that you see here represents an end of a year, right? And now we take our input value that sits somewhere on this timeline, and I want to go ahead and compute the closest end of year with respect to this value, right? So what I will do is I will pick some end of year from the past. It could be any end of year as long as it's in the past. Then I will compute with a simple dateDiff function how many years between the source year and the target year. Let's call the difference D. And now if I go ahead and add D years to the starting point, which remember is an end of a year, I'll naturally get positioned on the end of the target year, right? That's the sort of logic. So let's go ahead and implement it. So remember, we first say date diff in terms of years between some last year date. So let's pick one from the past. And our target date, which is this value. So this is how many years we have between the source year and the target year. Now let's go ahead and add exactly as many years as the difference that we just computed to the very same starting point that we used to compute the difference. And as you can see, what we get is the respective end of year date. So, you know, it's not an overly complex computation, but still people looking at it, let's say it won't be straightforward for them to figure out, hey, what we're doing here is computing the end of the year. So naturally, as developers, we like to encapsulate logic. We like to take complexities and hide them so that code would be more natural, more easy to maintain, and so on. So this is what we're about to do. We're about to go ahead and create a function called end of year, let's say we call it. Let's just make sure that we don't have one already. Right? And then we will create our end of year function that accepts this sort of input parameter, and it will return same data type And what we have within the function is we have just one return clause that contains this very same computation that we just had before, right? So now we are going to return the end of year for the input value that will be given to the function, right? So if now I will go and say, maybe I should add an S in the returns. And we have it going now. So now I will go ahead and say, go and return the end of year for my input value, whichever datetime value it is. Let's say it was 2014, February 12, then you can see how it computes the end of year. So now let's try two things. First, let's try to have our original computation embedded directly within our query, look at the performance of the query, and then see what happens when we go and replace that computation with a function, right? So let's go ahead and take the original computation and embed it directly in the query filter, only of course referring to order date as the date for which we evaluate the end of year. Now let's go ahead and run the query and measure the performance here. For this, let me go ahead and turn on statistics time so we can see exactly the time in milliseconds that it takes to process the query, and we'll have the query execution plan turned on. So as you can see, the query finishes in very little time. It's not even 1 second involved. Now, just to make sure that we do fair comparison between solutions, depending on whether I prefer a hot cache test or a cold cache test, either I run my solution twice and measure the second run time, or I clear the cache before I run both solutions. Let's say that we want to do a hot cache test. So second execution, as you can see, very, very quick because all the data is in cache. You will see a nice parallel query plan. You can see the exchange operators, and you can see the yellow circle with the 2 arrows telling you that the operator is a parallel operator. So we had nice usage of parallelism here. 1 million rows scanned using a parallel scan. And then as the data is scanned, it's also being filtered. You can see the predicate is evaluated as part of the scanning process. And then the remaining rows, as you can see, we don't have too many remaining rows, is under 3,000 rows, need to be gathered in order to return that unified set. What was the processing time involved? We can see in terms of net CPU time, it was close to half a second. And in terms of elapsed time, because we had multiple threads working, you see the elapsed time was actually shorter than the total net CPU time. So about 1/4 of a second, let's say. Now, after we went ahead and encapsulated the logic in the function, let's go ahead and see what's the effect when we use the function instead of the original computation. So we go and call the function. There's no question about the benefit in terms of programmability, right? So the query is much shorter, it's much cleaner, much easier to maintain. But then let's see if there's any effect on performance. So we go ahead and run it. And as you can see, it took 3 seconds to complete. The data is obviously cached already from the previous query executions. It took 3 seconds for the query to complete. Let's just check exactly how much elapsed in CPU time. So in terms of elapsed time, you see 3 seconds instead of 1/4 of a second that it took before. So we're looking at over an order of magnitude. It's about an order of magnitude difference. And in the net CPU time, it went from 600 milliseconds it was to also 3 seconds of net CPU time. It's a lot more work, no question about it. So our intuitive expectation is for SQL Server to somehow look at this function, realize that it's based on a single expression, and somehow sort of inline the function. But it seems like it's not doing this, right, you see?
Correct,
so
yeah.
What's going on here?
Well, one is today we don't have the concept of like an inline scalar function. Because if you look at the table valued function, there is specific syntax where it's an inline version versus a
right, so it doesn't have a body.
Version.
It doesn't have a begin
it doesn't
end.
have a body. Right. So basically, in this case, all the optimizer sees is like a function call, right? It's like a black box. It doesn't know what it is.
So it's actually executing the function.
It's actually executing that
a million
per
times,
row,
I guess.
Per row.
So we can see Well, first interesting thing that we see in the difference is already that there's no parallelism.
Parallelism, yes, because once you put a scalar UDF, you don't get
parallelism preventer.
It prevents parallelism.
And then we get a million rows flowing here, and then the filter actually invokes the function.
Yeah, because it's a scalar UDF and it gets applied at the end.
Right.
Essentially, you are always scanning the data, returning it to a next operator, which filters the value.
Right.
So that's where the...
So for you to actually add somehow a sort of an inline scalar function would mean one of two things. Either inventing new syntax that is more similar to the inline table function.
Just like the inline table function.
That doesn't have a body.
Yeah, basically instead of returning a table, it says return
an expression
type and then just have the return. That's one way to
Or what I guess is more complex to spot that the function, even though it has a begin-end, is with only return something and somehow internally.
Yeah, if you have just one statement, probably just go and take that and put it in the body. So today we don't look in depth into the function definition itself.
Right.
So that's really why.
So the reality is that, as you can see, the engine doesn't do it itself. The engine doesn't have at the moment a mechanism to see, hey, we have a scalar UDF that even though it has a begin-end clause, it has a return of one expression and no real other elements, so let's make it inline. It just doesn't happen. So the reality is that we pay extra for every row the function is executed, and then it accumulates to what you see here, plus the parallelism prevention. So how do we fix this? Well, remember our rhetorical question? The apply operator, of course. So what we do is we essentially convert the scalar user-defined function to sort of an inline table valued function, right? So remember, in an inline table valued function, we do not have a begin-end clause. We just have a return clause, but then again, we cannot return a scalar expression. We have to return a table. So the question is, how do you cause the function to return a table when what we are truly returning is a single expression? Well, we simply add a select clause. And now it became a query. Only we need to give a name to the target column. So let's call it something like R for result. And this is essentially just like saying select something, saying select 2006 as order year. This is, in T-SQL at least, a syntactically valid query. It's as if we are querying an imaginary table that has only one row, right? So that's essentially what we are doing within the function. So let's drop the existing version of the function. We say drop function end of year. And then we go ahead and recreate it as a table function, right? And now the question is, how do we embed it in the query when the function is not a scalar function anymore? We can't just refer to it like a scalar expression. Well, the answer is, of course, apply. So what we will do is we'll either use the explicit version of apply or the implied version of apply. For the let's see both actually. So let's take this query and first look at the explicit version. With the explicit version, we say cross apply. Now have the function moved here, right? And then we'll name it somehow. Let's say F for function, and then we will go and compare the order date with the returned element from the function. Now, what would probably make your code much easier and much cleaner is if you use aliases and prefix all of the elements. Of course, here we have unique column names, so it's not necessary, but still, it would make cleaner code, I guess. So let's name the orders table O, and ensure that everyone knows that we're collecting the order date from the O instance, and that order date here is also from the O instance, and R is from the function. And now, from the O instance, we can return, obviously, whatever it is that we like. So this is how we convert the use of the scalar user-defined function to the inline table valued one. Now let's go ahead and run this and see the effect. It's already over. So it finished, and the reason it finished is because, like any inline function, it got inline this time, and internally it got converted to the original form of the query that had the inlined expression. And you can see the query plan. We have a nice parallel execution plan. It's identical essentially to the plan we had originally, and therefore the numbers will seem, as you can see, very similar. So this is how we use the explicit apply to fix this problem. As for the implicit apply, as long as you need to refer to this element returned by the function only once in the query, you might as well use the implied version of apply by saying select that column from the function using a subquery. Now it turned to be a scalar subquery, same kind of concept like apply, but after the inlining, as usual, we get the same kind of execution plan that we had for the original query, and you can see also finishes instantly, same kind of plan, same use of parallelism, and same or similar, of course, numbers, right? So this is what I see today as one of the sort of main use cases for apply in the context of scalar use-defined functions, converting them, as long as they are based on a single expression, converting them to the inline table function form, and then using a cross-apply to activate them. All right, so it's not, let's say, a perfect workaround, but it's certainly better than not having any workaround. Right? So this pretty much concludes the second segment about improving scalar use-defined functions using the apply operator. So now we move on to improving a feature that was added in SQL Server 2005. So one of the biggest and most important features in SQL Server 2005, well, actually 2005 had so many fantastic features.
New features, yeah.
You know, I think it was one of the best developer kind of related features.
Yes. Yeah.
All the ranking functions, apply.
Apply operator was there
in 2005. What else was there?
All the window functions, basically.
Yeah, the windowing concept. Yeah. Partitioning itself, right?
Pivot, unpivot.
Pivot, unpivot. Wow, man. We need another release like 2005. 2016. The next best developer release. So anyway, SQL Server 2005 introduced partitioning for tables and indexes, a very strong feature. And in this segment, we're going to look at a certain class of queries, or certain kind of very basic calculation that with partition tables and indexes simply doesn't get very good performance. And then we'll see how we use the apply operator to essentially fix this problem. So let's first go ahead and look at the basic aggregate query that does a min or max kind of calculation, and then we'll have a look at what happens when there's partitioning involved, right? So let's just pick any kind of table that has an index on one of the columns. So here's what we'll do. Let's query the orders table and request the maximum order date from our orders table. Right? So let's do the same for max and min. All right, so let's look at the query plans for these queries. What you will notice is, as long as you have an index on the aggregated column, you will see that the plan starts scanning the index either from head forward or from tail backwards, depending on whether you're asking for a min or max. The way you can tell if it's ordered forward or backwards is simply by looking at the properties of the scan operator, and then you will notice there is this property called scan direction. So in the case where we ask for a max aggregate, the plan starts with the tail of the leaf of the index and then starts going backwards. And in the case of a min operator, then we have something very similar, only we start with the head of the linked list, and you can see the scan direction is forward. Now, something that shouldn't confuse you is that we're not really getting a full scan of the index. Rather, something very interesting about the way people tend to analyze query execution plans versus the way in which they get internally executed. So for most people, the intuitive way to look at a query plan or analyze it is in the data flow order. Like you can see, we have those arrows that represent the data flow order, and it's kind of natural for people to also analyze the plan like this. So they, in their mind, will look at the scan operator as the first thing that is executed, and then rows are flowing to the top operator and so on. But in reality, the internal API call order actually starts with the root node of the plan. So that's the leftmost node that you can see here. It invokes an API that requests a row from this operator, which invokes an API that requests a row from this operator, and so forth. So it's the top operator that actually drives the request to return rows from the scan. And you can very clearly see in the top operator under actual number of rows that the number of rows that it requests is only 1. So that's how you know that what we get is not a complete scan of the table because the top operator stops requesting rows after it got the very first. And therefore, we get the min or max with very, very little effort, just starting to touch data and we're already done. So this is how you would normally expect max or min aggregates to be optimized. Now, let's see how things look like when we have a partitioning involved. So what I have here is I have a partition table. Oh, I went very far ahead. So we look at the 2005 section, and you can see here we have a database called test min max, right? And within this database, I already ran the code that creates and populates a partition table called T1. And you can see I'm using a partition function that splits to 5 partitions. You see 4 boundaries. We have about 1 million rows in the table, so you can see around every 200,000 of rows that we have in each partition. And our table will have 2 indexes. One index is an index created on the partitioning column itself. So you can see column 1 is our partitioning column, and we have an index called IDX column 1 based on this partitioning column as its key. And then we have another index. That other index, column 2, is created on column 2, which is not a partitioning column. So, I mean, a simple way to visualize this is if we look at the B trees, and we have now 5 sections, 5 partitions in our table. What's interesting for us to remember is that the index on column 1, we will have those small B trees because we have a separate kind of B tree created on each of the partitions when we partition the same manner as the table. But then with the index on column 1, it's very clear to us that the minimum value will necessarily be the minimum value in the first partition, and the maximum value will be the maximum value in the first partition because we partitioned by the same column that we indexed. Now with the column 2, the situation is different. The minimum value for the column 2 could be in any of those 5. We really can't tell for sure ahead. Same thing with the maximum value could be in any of those 5, smaller B trees. So obviously it's a bit tricky now for the optimizer to figure out how to collect the minimum or maximum when we ask for it from the column 2 values and not from the column 1 value. So notice what happens when I go ahead and write a query that says, give me the maximum column 1 value. Here we should be able to get a very efficient plan. So notice the query plan. Let's also maybe look at the amount of work involved. So we'll turn on statistics, IO, as well as time. And then let's look at the amount of work involved here. So first of all, look at the query plan. You will see, notice, actual partition count. You see how many partitions are accessed to process this query? Only 1 partition. In the case of the max, it will be the last partition, of course. And you will notice that, again, the same top operator that we discussed before goes and requests only 1 row. So the very last partition's B tree for column 1 is being scanned backwards, and the first row that is accessed, that's the maximum value, and the work simply stops. So in terms of IO cost, you can see there wasn't too much work involved. In total, in terms of CPU cost, also very, very minimal. But then try the same thing for column 2, and now here's what many people would expect but doesn't happen because it requires extra logic to be embedded in the engine that at the moment wasn't. Many people will intuitively expect the optimizer to go and do a similar kind of activity that we just saw for column 1, but pair a partition, right? So if you have 5 partitions, you would expect the index to be scanned tail backwards with 1 row from each of those, and then kind of do a global aggregate on top of the local aggregates for the partitions. But unfortunately, this doesn't happen. And notice what does happen. Well, what happened is, behind the scenes, the optimizer just decided to do full scans of all 5 partitions It seemed to finish a bit quickly just because all of the data was in cache and we still have only 1 million rows in this table. So it's not overly large. But you will notice actual partition count is 5. And this time there's no top operator involved that tells the scan to stop scanning after some rows. We simply scan all million rows that we have in the table and then apply the aggregate on top. So you will notice the amount of work involved compared to the 3 reads that we had before. Yeah. Even if we multiply them 3 times 5, you would expect to see about 15 reads. Unfortunately, you see this a very inefficient full scan. And accordingly, of course, we have some more significant CPU work, which was close to 0, if you recall, in the previous case. So, question is, what do we do to solve this? So remember our rhetorical question. So operator. We have apply operator, of course. So here's the trick. The way we do this is, you will notice that if we go and filter from our table only 1 partition's worth of data, simply by using the $partition function with the partitioning function that we use, and filtering only 1 partition. So $partition.pf1, which is our partitioning function, providing column 1 as input, equals 1 means show me only the rows from partition number 1. And here you will see that the optimizer is smart enough to realize, hey, I'm going to have only 1 partition involved, so I might as well think of it like I had only 1 table and an index that, of course, is based on the table. So we go back to the original kind of strategy that we had with no partitioning at all. So knowing that the optimizer can do this well for a single partition, how about if we go and query the different partitions that are involved in our table or our index? So we could pick any index that is partitioned based on column 1. In this case, because we are hoping to get the index called IDX col2 to be used, might as well use this one as the one that we collect its metadata for the list of partitions. So we select from syspartitions the numbers of the partitions that are related to index 2, and this query would give you just partition 1, 2, 3, 4, 5 when we have 5 partitions. And then using cross-apply, we go and activate the very same query that we saw running against a constant partition number, this time against the partition number that we collected from syspartitions, what we refer to as P. And notice what kind of plan we're getting now. So exactly the kind of plan that we were hoping for, besides the fact that there seems to be a lot of mess that is related to constructing the syspartitions view. But if you think of all of this part of the work as very, very little work, in fact, collecting just the list of partitions from the syspartitions table, the rest is the loop that runs once per partition and then activating exactly the same logic that we were looking to get, and that's for partition 1. We go and collect from the index on partition 1 the maximum value. For partition 2, we collect the maximum for partition 2, and so on. And once we get 5 values with 5 maximums, you see the kind of aggregate on top of those individual aggregates. So, of course, as a result, we look at the amount of work against the T1 table and notice this. We have in total only 10 reads. And of course, CPU time dropped significantly. It seems like close to 0, basically, CPU time that was involved. So you see, I'm guessing this is one other example of things that the optimizer could do but currently doesn't do. Is this something you got frequently from customers? Kind of partitioning related optimization?
Yeah, things? I mean, I believe we have some of these requests, but I mean, generally partitioning is not a commonly used feature because it's more like a management related and depends on the size of the databases and so on. Yeah,
but for big customers, I guess it's kind of a common thing to use.
We could definitely add it. And the other thing I think we could, instead of querying syspartitions, you can also query the partition range values.
Right.
That's
for the function.
For the function. That's another way to see if that metadata will be typically smaller than partitions.
So the efficiency here would be going against a smaller kind of metadata source.
Table than that, or even like a fixed, like a getNums function.
You could use a getNums or values clause.
Yeah, so there are many ways to kind of, I guess.
But I'm guessing partitioning added quite a lot of complexity in general to optimization. So like things that work in a quite straightforward manner in a normal table, then there are extra complexities around
And also,
partitioning.
like as the number of partitions increase, then the memory requirement for the query increases.
Right.
So that's one of the challenges. Like if you are restricted to say 500,000 partitions, then there is less metadata to go and look in terms of how the index is organized. But with 15,000 partitions, then the memory requirements become huge.
Right.
So yeah.
But at least we have a workaround.
Yeah.
Thanks to apply, obviously. All right. So this pretty much concludes the third segment about how to use the apply operator to improve a certain class of queries against partition tables, specifically the simple min or max aggregate that is applied to a column that is not the partitioning column. Because recall, when the column is the partitioning column, anyway we get an optimal plan, right? All right, so we proceed to the fourth segment, and that's a feature that was introduced initially in SQL Server 2008. It's a very cool feature, and the thing is that there are certain ways to use it to extend the capabilities of SQL in general, I would say. So we will look at two main kind of use cases. We'll start with a reuse of column aliases throughout the query. First of all, we will discuss a certain limitation that we have generally in SQL, why this limitation exists, but then how we use apply combined with values to solve it. So first of all, I want to just introduce this values clause, then introduce the problem, and then the fix. So the values clause is something that we normally use in insert statements, right? We issue an insert into some table. Let's say we had a table of years or something. So we would say select into years, and let's say we have a column called order year. So here we would say values, and then let's say the year 2012, and then you would need another row for 2013 and 14 and so on. So one of the improvements that we get in SQL Server 2008 is that based on a standard feature called table value constructor, also row constructor, we can extend the values clause to define not just one but multiple rows. I think there is a limit in SQL Server, right, for something like 1,000 rows.
Yeah, I mean that's
for
more
values,
because we kind of translate it to like a union.
Right. So you internally,
expression.
You internally translate it to something like this:
Select
2012.
Yes, union
As order year, and then union all.
Yep. Yeah, it's kind
So
of
this is the reason you say for the limit of 1,000, right?
Yeah, I mean the limit is more to kind of optimize the execution for the values.
Right.
Constructor.
Yeah. So like UC says, basically internally the values clause is internally going to be translated to something like this. So instead of writing 3 insert value statements, we will simply go ahead and add multiple rows, right? We will say 2013, 2014, and so on. And this internally gets translated, like UC says, to the union all construct. So that's one benefit in the values clause. The other benefit is, just like here, we have a query that generates a table, conceptually at least, we could use the values clause to define a derived table. So we would start the derived table here, end it here, give a name, let's call it years, and then give a name to the target column. And basically, this is now the equivalent of the union all query that you just saw. So we can now basically have a query that says select order year from this kind of special derived table, right? So that's in essence the values clause. One, we use it in insert statements to insert multiple rows up to 1,000 for now. And then we could use it to define a derived table based on those expressions. Now, most people use the values clause in the context of a constant expressions, just like I did here, years or whatever. But you realize that using the apply operator, if I use apply, I expose to a table expression all the elements from the left row. So in essence, the values clause could have references to elements that I collect from the left row. So this way, I'm not going to be limited to constants. I could refer to any elements that exist in that left row. So just keep this idea in mind. We will get back to it later. For now, let's first talk about a certain restriction or a certain limitation that we have in SQL in general, not just T-SQL, but standard SQL, and then we see how we use these values close to overcome this restriction. So here's the issue. Let's say that I wanted to write a query that performs some kind of a computation. Yeah, let's say I wanted to say select order ID and maybe the year of order date as order year from my orders table, right? So we just created the column from a computation, right? And then there's this very classic thing that people try to do but are not successful in this, and we'll try to understand why. Yeah? People will try to then refer to this column alias that we just generated elsewhere in the query. For example, if I went and said where order year is greater than some year, let's say 2006. What happens when I try to do this? So, many people look at this and say, hey, first of all, they think maybe they had a bug in their code, maybe they mistyped the name of the column and so on, but then they realize the column name is certainly identical. We can even do copy here and paste here, and still it would not work. And it just says, there's no such column called order year. So, is there something in the standard that somehow explains why this doesn't work? Something in SQL?
Yeah, conceptually a SQL statement returns a table.
Right.
So the table columns has to be kind of materialized first in order to reference it.
All right.
And if you're in the same query context, then if you are deriving new columns or projecting new columns, then you cannot really reference it in the where clause, or the only clause you could reference it is the order by.
Right, so maybe another way.
Conceptually at the end of everything.
So order by is evaluated after the table result was already generated. Yeah. Yep. So maybe another way to look at this is with something I like to call logical query processing that says, let's try and visualize the sort of conceptual evaluation of our query clauses. And even though we type the query clauses like this, select from, where, group by, having, and order by, this kind of order is more similar to the way we give instructions in English, right? So, for example, in English, think about if I wanted to say, give me the cup of coffee from the table, then I started with the object and then I talked about the location of the object. So that's how we give instructions in English. But if I wanted to write down the instructions for a robot, let's say, that doesn't have any kind of language intelligence, I would need to provide the instructions closest to the order in which they need to be carried out. So while the typed order of the clauses is closer to the way we would make the request in English, the internal interpretation order, still the conceptual one, we don't necessarily talk about the engines, treatment yet, but the conceptual processing of the request has to start with the location before we can talk about the object. So we would tell the robot, go to the table, pick up the cup of coffee and bring it to me, something like this. So in a similar sense, even though we type the select keyword first, the evaluation, the conceptual evaluation or the logical query processing has to start with the tables that contain those elements that we want to return. So we would start with the from clause where we indicate the tables and table operators, including apply, and keep this in mind. Then we proceed to the where clause where we filter rows, then group by where we group them, then having, then comes the select. Only then comes the select. And then if we need any ordering elements, an order by would appear here. So if we go and define something here we had some kind of a computation that assigns this alias order year, it cannot be visible yet to all those previous, phases, right? It can only be seen by subsequent phases. So of course, the order by will be able to refer to this order year, but not phases before, right? Now, there's another interesting, so this explains why we cannot refer to order year in the where, in the group by, in the having, and so on. But there's another thing that SQL doesn't allow for different reasons. So, for example, if I try to do something like this, order year plus 1 as next year. Now, seemingly, I should be able to refer to this order year because I'm trying to refer to it after it was defined. But still, there's another very kind of special concept in SQL that you can think of as the all at once kind of concept that says that within the same logical phase, like the phase that evaluates the expressions in the select list, all expressions get evaluated in a sort of all at once manner. So if this is evaluated in an all at once manner, there's no relevance to the order in which those expressions appear. So therefore, even though the order here was evaluated in an expression that appears to the left of the one that tries to use it, it's still not visible to it, only to subsequent phases because of this all at once behavior. So this is the problem. The question is, how do we solve it? So what many people will do is they will solve it by using a series of CTEs, like CTE 1 that goes and here defines one alias, right? And then CTE 2 that defines another alias based on the first, like here I could define order year, and in the second one I could define next year, and so on, right? And eventually, you know, the outer query will be able to refer to all of those aliases, right? But, you know, it can get ugly very quickly when we start building CTEs on top of CTEs on top of CTEs. So remembering that the cross-apply operator is a table operator, meaning it is evaluated in the from clause. And recall, in logical query processing, the from clause is the first to be evaluated. So anything created by the from clause will naturally be then visible to all remaining clauses within the query. Furthermore, each table operator starts a new set of logical phases. So what one cross-apply creates naturally is already visible to all subsequent table operators. So if I wanted to build expressions that are very, very long and complex in steps, there's no problem for me to build them sort of gradually by aliasing one of the parts of the expression in one table operator and then already referring to it in the next one, right? So it's a much cleaner and much more elegant way to do this. And also remember what we discussed about the values clause. The values clause with cross-apply is allowed to refer to anything that appears in the left row. So if I'm operating on a table called sales orders, then naturally anything that appears in the order row is visible to me within the values clause. So that's the main trick that we're about to rely on. So let's go ahead and try and fix this problem that we had before. We'll name the orders table O, and then here we'll say cross-apply. And then here we'll create, let's call the apply table expression A1 because we can have multiple ones. And then using a values clause, I'll now go and collect elements from O. So for example, I could take this computation, move it here, and then have the alias that I assigned applied here. And again, it's not a must, but I suggested earlier for cleaner code to make it clear to everyone which source table we collect the column from, of course, a good idea to go and provide the prefix. And now the benefit that we got from this is that the order year alias was generated already by the applied A1 operator, and therefore all subsequent clauses are already allowed to refer to it. Certainly the select clause, but if here we had the where clause, it would now be allowed to refer to this order year, what we couldn't do before. So for example, this works no problem. And now how about the issue with all at once? We could use a very similar solution basically. We could add another cross-apply. We cannot do this in the same cross-apply because this next year relies on the alias order year, right? So still we would have the same all at once issue. But a subsequent table operator is already allowed to refer to elements that were created by a previous one. So add another cross-apply, and then we create a second a table expression called A2, have a values clause that generates the expression. So here we'll take order year plus 1, place it here, and then over here go and assign this alias. And now with the much, much cleaner code, you can see we're both able to refer to this order year in our filter, even though it's a result of a computation, and we're able to refer to this order year in another table operator that went and generated the next year, and then of course refer to next year anywhere we like within the query. All right. So fantastic feature because it basically overcomes this very kind of annoying, I would say, limitation. I think that there is some feature that was kind of suggestion by the standard for some kind of a clause, a filtering clause that would be evaluated after the kind of table result is generated.
Correct. Yeah, right? I believe the newer standard has something like this.
But, so this would be so nice.
Yeah, we haven't looked at it.
Right.
And, I think Teradata has some feature also.
Right. I think it's called the qualify.
Or something. Yeah. Yes. They have some similar filters. And
so essentially, after the table result is generated, you are already allowed to refer to aliases that you defined there. Yeah.
And also some databases which are not strictly SQL and C-SQL compatible, they allow such things. Yeah.
But at least it's a fairly simple walkaround. That's the sort of good news, you know, that using apply is a fairly simple walkaround that we have here. All right, so this pretty much concludes how to use the apply operator combined with the values clause that was introduced in SQL Server 2008 to simplify a number of things, reuse of column aliases in our query. And then the second part of the very same segment, I wanted to show also another use case for combining the cross-apply operator with the values clause to solve some complex unpivoting tasks. So it's still part of the same segment, but just a second use case. So let's say that we have the following situation, right? We have a table called sales. Let me just fill it with some data. And then let's have a look at the data in this table. So I created it in the MongoDB database. So select from sales. So what we have here is kind of classic spreadsheet-like representation of data where we hold one row per customer and a set of columns for quantities in different years and a set of columns for values in different years. Now, this is typical representation of data in spreadsheets. And let's say that we just went and imported the data from a spreadsheet into our database. And obviously not very convenient to work with the data in this manner. When we want to go and apply data manipulation, it's much easier for us if we have a row per customer in year, and then one column for the quantity that year and one column for the value that year, as opposed to just one row per customer, right? Just not too convenient to work with the data like this. So our goal is to do what's known as unpivoting. We want to sort of rotate the data from its current state of multiple columns in one row to a state that has just two columns, one with the source column names, like the years in this case, and one with the source column values. And in the case of another set, there will be another one with the source column quantities, right? Now, there is a native operator in SQL Server that was added. It was in 2005, right? You see, you added the pivot and unpivot. So there is this native operator called unpivot. It's not standard, but it's a native kind of language within T-SQL to say unpivot this data. The thing is that it's restricted in the sense that it can only cope with one set of columns that need to be rotated. But you see, in our case, the unpivoting task is more complex in the sense that we have two sets of columns that need to be rotated, and the unpivot operator simply doesn't know how to cope with this. So our goal is to do this sort of multi-set unpivoting, have the result with a column with years, a column with quantities, and a column with values. So we cannot do this with the unpivot operator, but remember our rhetorical question, which operator will allow us to do this? And that's, of course, the cross-apply operator. Now, let's see how this is done, combined using the values clause. So I will go ahead and do a cross-apply. And then recall that what I'm about to apply, if it's a values clause that constructs a derived table, then I can refer here to elements that I'm collecting from my sales table. Now, I want to create 3 rows from each source row, one for 2012, one for 2013, and one for 2014. And in each row, I want 3 columns. The one with the year, the one with the quantity of the relevant year, and the one with the value for the relevant year. So what I will do is I will name those target columns order year, then the quantity, then the value. And then let's start constructing 3 rows from each source row. So we should have 3 such rows. That's 1, 2, and 3. And each of them, remember, will start with a year. So we'll just put the constant 2012, 2013, 2014. And then the next part is we're about to start collecting actual columns from the left row. So for the row for 2012, I will collect the quantity 2012 column. And for the value, of course, the value 2012 column. And in a similar manner here, for 2013 and 14, I will just collect the columns from the respective year. And it's so interesting to try and visualize this, how we took this one row and basically with cross-apply ended up sort of turning it into 3 target rows. And then, of course, from the left side, from sales, I can collect the customer ID. And from the applied side, I can simply collect everything because we listed those column names explicitly. And notice what happens here. We ended up from each source row generating 3 target rows, one for 2012, one for 2013, one for 2014. Also nice to look at the query plan, highly efficient query plan. The constant scan operator is the operator that builds kind of a table from constants. So each source row is being turned into 3 rows and then internally like a cross join that happens between it and the underlying row in order to be able to return elements from both sides. So, in this case, the table is very, very tiny, but when testing it against much, much bigger tables, the performance is really quite amazing compared to other solutions that can be used here. Right? So simple, straightforward. Of course, once you start getting comfortable with the apply operator, you will find yourself naturally coming up with such solutions, right? So this pretty much concludes the section that describes how to use the apply operator combined with the enhanced values clause, the one that was enhanced in SQL Server 2008, to solve both issues with reuse of column aliases and how to solve more complex unpivoting tasks that the unpivot operator simply doesn't know how to cope with. All right, and then we move on to our last segment for this course, and that's how to improve a feature that was added recently in SQL Server 2012. That's a feature called offset fetch. So the offset fetch feature, I'm going to show how to use it to solve a classic kind of statistical calculation called median. But first of all, maybe a couple of words about what the offset fetch operator is and how it is related to standard SQL and so on. And then we'll see how to use it along with apply to solve a certain problem. So what is this offset fetch operator? Let's go back to our T-SQL 2012 sample database. Let's say that I wanted to return the 3 most recent orders generally from my orders table. Remember that we could always use the top operator to do this. So I'm returning some elements from my orders table. And then if I wanted to return only the 3 most recent based on, let's say, a date and then order ID ordering. Right, so as you can see, we got the 3 most recent orders. The top filter indicates how many rows we want to return. The order by clause indicates, in this case, both the order for the filter to know which 3 rows to pick, and then also serving its classic kind of use, which is presentation ordering. So we are also guaranteed the rows will be presented in this order. Now, the one thing the top lacks is the ability to indicate first how many rows we want to skip before we indicate how many rows we want to filter. And the classic use case is what's called paging or pagination, which many applications support. So think about internet stores, search engines, and so on. So you search for something, you get the result, but the full result set is simply too big to fit in one web page or one screen. And then many of those applications will give us some kind of paging capabilities. So we can ask for one chunk of the rows at a time. And top simply doesn't have this capability of saying, hey, I first want to skip that many rows before I filter, that many. So instead of the top, we now have this so-called offset fetch feature. So the way it was designed is, first of all, unlike top, the information here about how many rows to filter and based on what order is not split to two different clauses, right? It's all connected directly to the order by clause. And in addition, what top doesn't have is the ability to first say how many rows to skip before we indicate how many rows we want to fetch. So if I want to, let's say, return the first 25 rows, I don't want to skip any, I will say offset 0 rows, and then fetch next, and then how many rows I want to filter, so rows only. And now I will get the first 25 rows, which is identical to saying top 25 when I don't need to skip anything. In fact, it will be optimized the same way as top when we don't skip anything. But then if I'm after the next page, I can say skip 25 rows before you filter the next 25. And then when I want the next page, I will say skip 50 rows before I fetch the next 25 rows, and so on and so on. Now, unlike the top, if I use the top operator, the order by clause is actually optional. I could say select top 3 with no order by, and then I'm going to get some 3 rows. I don't know exactly which 3, but I'm allowed to say give me some 3 rows. With the offset fetch, it's actually in T-SQL at least mandatory to have an order by, right?
Correct, yeah.
So is this a standard requirement?
No, it's a basically implementation restriction at this point. Because one of the challenges, if we make order by optional, then we had to make offset as a reserved keyword. And that's a very common name in terms of column names, right?
Right, right.
And that would mean like even our own system stored procedures, there are some procs and stuff which actually use that name as an identifier.
And if I remember correctly, the standard actually allows omitting
both.
The
basically, it's a totally different clauses. So you can specify one or the other.
Right.
And order by is not mandatory.
Right.
But
so why is the offset mandatory? So you explained why the order by is mandatory, but why would the offset clause be mandatory? Why not allow this? Order by and then fetch next 25 rows only?
Because we have a fetch statement in SQL Server already.
That's for cursors.
The cursors.
Right, so you wouldn't know.
It kind of, and we don't have statement terminators is not mandatory.
Right.
So it's kind of hard to figure out if it's really a fetch statement for a cursor.
Yeah, so you don't know whether to connect this to the previous statement
order by or
start a new statement. That,
offset is a new, like a contextual keyword, and
right.
We know that it's not a valid, it's not some other statement.
That's clear.
But
I'm guessing it is a best practice
to
terminate everything and make it easy for you to go and add features that won't be so hard to parse.
Yeah, correct.
Yeah. Are you planning to make it mandatory at some point?
No, not
I'm
right now.
sure many people are
interested. Because it requires a lot of changes for customers to go and change their code.
Right, but it is a very, very important practice, let's say, to terminate all your statements with a semicolon, and then at some point in the future, when Microsoft will see it's a common practice, of course, will make it so much easier for them to add new features that don't involve parser complexities.
Or even when we add certain new features like merge, for example, it requires terminators.
Yeah, so some of the new features already make it mandatory.
So it's, as a good practice, it's just always better to
always
terminate.
All right, cool. So that's essentially our offset fetch filter. And now that we understand the feature itself, let's talk about a kind of classic task, and then the ways that we have to solve it, and then how we solve it using the offset fetch and the apply operator combined. So the task in question is a very classic task computing a median. So median is a statistical calculation, more generally known as percentile. But specifically with median, it's what's called the 50th percentile. That's essentially the value from the set below which 50% of the observations fall. Or if we wanted the 25th percentile, it would be the value below which 25% of the observations fall. So let's say we have a table T1. That's a new statement, a new clause.
Frame.
So we have a table called T1, and the table has, as you can see, some kind of a group column. It could be anything. It could be a customer. It could be a test. It could be anything that represents the group. And then we have some kind of a value column representing some sort of a measure. Could be a score in an exam. Could be, age, whatever. And now, in a median calculation, our goal is to go and identify the 50th percentile within the values, right? So remember, the value below which 50% of the observations fall. Now, in statistics, there are two distribution models that we could use for percentile calculations. One called discrete and one called continuous. So the difference between them would be, let's say we were working with group 1 and we looked at the data sorted. Yeah, let's just make sure that we show it sorted. So order by GRP and then value. Then the discrete model must return a value that exists in the population. So for the 50th percentile, it's easy. When we have an odd number of elements, it's clearly simply the middle point. The problem is more when we have an even number of elements. There's no exact middle point. And the discrete model says it has to be a value from the population. So the discrete model would return the closest one, right? So in this case, it would be 60. We have kind of equal distance from both sides. Then the continuous model essentially assumes that we have continuous distribution of the values even in the gaps that we have between the existing ones. And therefore, we can interpolate the non-existing value from the two that appear around it, basically. So in the median case, it's quite easy. It's simply the average of the two middle points. Yeah, so in this example, it would be 62.5, right? Now, SQL Server 2012 adds windowed forms of percentile calculations. In standard SQL, actually, it's supposed to be implemented as an ordered set function, right?
Correct,
where we say group by, and then it looks like a group function.
It's like a,
yeah.
Like
so let's first look at how it is supposed to look like in the standard,
Sure.
and then we'll see how it was implemented in SQL Server. So in the standard, you would say group by, and then your column, GRP, and then for each group, you would say now percentile. And now, depending on whether you want to use the discrete or the continuous model, let's say in our case, we want the continuous model, you would say cont, then you would specify which percentile. So median would be 50th percentile. And now you would say, and that's the part that makes it what's known as an ordered set function. You would say within group, and here you would define the order, because this percentile function has to be based on some order. So order by, and then we have the value column that defines the order, and this would be your median. The thing is that we don't yet have an implementation of ordered set functions within SQL Server.
Correct.
So I'm guessing it was easier for you to first implement it as a windowed function
yes.
where you have the infrastructure, therefore ordering of the window.
Yep.
Yeah.
So we use that first.
So this would become essentially the partitioning element in the window, and then the window order would be the one. Yeah. So, but you still added this clause of within group only in the context of the windowed function. So
correct.
Something like this over, and then you would say partition by, and then the group column, and not a group by. So kind of difference between this and the original ordered set function is that a windowed function is not supposed to hide the detail like a group function does. So a group function would return only one row per group, whereas a windowed function would return the information in addition to the detail rows. So now we're about to get a row per source row and not a row per group. So it would seem a bit strange that we get the rows repeated, but essentially that's because we're not hiding the detail. So a simple option would be to use a distinct here, and then kind of getting rid of this, the duplicate. So I'm going to look at the query plan. I want to warn you a bit not to get alarmed.
Yeah.
It's going to be a bit long.
It's going to be having a lot of
The plan
stuff.
is huge. The plan is very, very long. So you can see, it goes on and on and on and on and on. And in two places within the plan, the data is collected from the source, stored in a spool that's essentially a walk table, and then the spool is read twice. Once to compute aggregates, and one for the detail
rows.
so not to lose the detail. And this happens twice within the plan. So all this simply translates to, unfortunately, quite a lot of work. So even though there are many very fantastic features related to window functions and a lot of very, very efficient aspects of optimization for some of them, specifically the ones that compute percentiles were not implemented too efficiently. Unfortunately, they don't get optimized, let's say, too efficiently. And as evidence, let me switch to a database that has 10 million rows. All right, so we had just 6 rows or 7 rows to show the example, but I'm now running the very same query against a table that has 10 million rows. So remember, we have the data scanned from those 10 million rows, stored within a spool, essentially a work table. In one case, I'm guessing what you do is computing a count.
Correct.
And in the other case, figuring out which rows based on the count you need to return.
Which detail row to go
right.
and compute the difference.
Yes, so you see this is going on and on and on and on. And while it is going, so we don't want to wait here too long until it finishes. While it is going, I'll write a different version of the solution, this time using the combination of offset fetch and apply, right? So in essence, what I'll do first, and again, we'll run it first against the smaller set to see the solution works correctly, then we'll try it against the bigger set. What I will do is this. I'll first go ahead and collect from our table for each group, let's group by the GRP column. For each group, I will collect simply the count of rows, how many rows in the table, right? So let's go ahead and look at the query plan also. So you see, I'm just looking at the count. We have 3 rows for one group, 4 rows in another group. You will notice that if we went ahead and created a good supporting index, for the count, all we need is just an index on the group column, but for the second part that does the actual filtering, we actually want an index on group column plus the value column for the offset fetch to be optimized efficiently. But so far, what we're doing is a single scan of the data just to compute the counts here, right? Now what I'm going to do is, based on the counts, I'm going to compute for an offset fetch filter how many rows we need to skip and then how many rows we need to fetch. So how many rows we need to skip is simply taking the count, subtracting a 1, and then dividing by 2 using integer division. So that's the offset value, right? So let's see, when we had 3 rows, we need to skip 1. When we had 4 rows, we need to skip also 1. And when we have, let's say, 11 rows, we need to skip 5. When we have 12 rows, also we need to skip 5. But then, how many rows do we need to fetch? This depends on whether the count is odd or even. So we'll take that count, do a modulo 2. This tells us if it's odd or even. If it's odd, we need to skip 1 row. If it's even, we need to skip 2 rows. In other words, it's 2 minus the parity. So now we have our fetch value. So you see, still without any significant extra work, you see the compute scalars that do these computations don't add almost any effort. Now we know exactly for each of those counts, for each of those groups essentially, how many rows we need to skip and then how many rows we need to filter. In the odd case 1, in the even case 2. Now, how do we make this filter work per group? Remember the answer? Is the apply operator, of course. So what we will do, we will go ahead, define a CTE representing those parameters or arguments. And now we will go and say select from C. And then we will go and perform a cross apply. And now this table expression A will go and return to us the interesting values, right? Let's just return the interesting values, or we don't even need to name them because they already have a name in the source. So let's go ahead and say this. Select from C, filter where the C GRP, or actually we need here to query the base table T1. And here we'll say in the filter where the T1.grp column needs to be equal to the C.grp column. So now we're focusing only on one group in each iteration. And what do you think? Should we keep the 2 where clauses or? No, maybe keep just one. So now we'll go ahead and add an order by clause, order by. And now remember, our ordering element is going to be the value. So this comes from the T1 table. So value. And now comes the offset fetch filter. So we'll say offset. And remember how many rows we want to skip. This is something we computed as the offset value here, right? So offset C.offset value rows, and then fetch next, and then C.fetch value rows only. And now the qualifying cases, we will collect from T1 only those relevant values, right? So in the select list, we will return from C the employee ID, and from the apply table expression A, we'll return just the interesting values. And you will notice that we get an error. Why? Because it's not employee ID, it's just the group column, right? Very confusing two tables. So here you can see when we had only 3 rows in the group, it was an odd count. We ended up with only 1 row in the result. When we had an even count, remember those 60 and 65? Those are the 2 middle points. And of course, the only thing left here is to go ahead, group by our GRP column, and then for each group, compute the average of the values. And this is our median. And why am I multiplying my values by the decimal 1 point? That's because if the source column is an integer column, the average will perform an integer average. And I want it to perform a decimal average, so either I explicitly convert the input to decimal, or I do it implicitly by multiplying it by a decimal value. And here's our solution. So let's see if the other query is done. So the other query is done, and it took it, well, you see, over a minute. It was 1 minute and 18 seconds. Now let's try our new one against the very same table. So it's in TestDB, and let me just make sure that we have the right index in place. So T1. So just to see that we have the very same index, you see the GRP val. So you see that the other query didn't run so long just because we didn't have the right index. We also have the index on the bigger table. And now, how long it takes this one to complete? It's done. It's just 1 second compared to 1 minute and 18 seconds. So beautiful solution, highly efficient. You see also very efficient treatment of parallelism. So for each group, we have a different thread essentially working on processing the data. So here at the bottom of the nested loop iterator, we have multiple groups essentially being processed in parallel. So a fantastic solution, highly efficient, the fastest that I know of today for median calculations. So all of the examples that I ran in this course, including the last one, I ran on SQL Server 2014, just to show all of those features are features that even if they were introduced very long time ago, like top and so on, are still very widely used today. And you saw how the apply operator could improve either their efficiency or functionality or both. So this concludes both the last section and also the second part of the course and the course itself.
Thanks everyone for attending the course on apply operator. I hope you learned a great deal about how to use it and to solve a lot of common problems that you would encounter. And you learned about the fundamentals of apply operator and how it works with other operators in the product. So feel free to check out other SQL Server courses in the Virtual Academy for other important features. Thanks.
All right, thanks, UC. It was really a fun session. And if you liked it, I also deliver a much longer 5-day advanced T-SQL class where I talk about the apply operator and many, many other cool aspects of T-SQL. So check out the website that contains the source code, tsql.solidq.com, and you will find information about